morning students. Today we will start the third chapter on quantum statistics, and I would like to highlight a few points that we are going to discuss in this particular lecture that will pave the way for more intense and deep discussions in the coming lectures. So, this is the first introduction to statistical mechanics of quantum systems. Now, the first question that arises in our mind is that why do we need a different level of statistics for quantum systems? Now, to understand that, we must first identify what is the quantum limit of any classical system, or what is the classical limit of any quantum system. That being said, we are looking at the same system, the system does not change, but it may so happen that for a combination of temperature and density, the system at our disposal may behave quantum mechanically, meaning that it is no longer representable by a deterministic set of rules, which means at some sufficiently high density or sufficiently low temperature. I will discuss in a short while what do we mean by sufficiently high or low. So, at high density and low temperature, you would replace classical mechanics with quantum mechanics, and we have already seen some kind of a discussion on the onset of quantum mechanics in classical systems. So, we will start off with a small recollection of the fact that, so first before we recollect anything, I would like to put down the points in some order, okay, just figuratively, to basically decide what we are going to discuss. Okay. So, the first thing on the cards is basically onset of quantum mechanics. So, when should I be worrying about quantum mechanical effects? That is the first thing to ask, because otherwise after chapter 1 and chapter 2, I know exactly what to do when somebody asks me to compute the heat capacity of a material or susceptibility of a magnetic system. All these questions can be answered using tools of classical statistical mechanics, but the same system at my hand, for example, electrons in a metal or spins on a lattice, will classical theories suffice? Will they give me the right answer? The answer to this question relies on the parameters of the system, the physical parameters of the system, which are the density and the temperature, and that should decide whether I am in the quantum regime or classical regime. We will discuss those parameters very shortly. The second point in this chapter would be basically a machinery or a theoretical set of tools that appropriately handles the system of indistinguishable particles. Now, you have seen in classical statistical mechanics, we do not know how to handle these indistinguishable particles except for the fact that once you complete a calculation, you account for the fact that microstates which are only different from each other in only permutation of identical particles are to be seen as just one entity, and so you in some sense plug the n factorial prefactor after you have completed your calculation. There is no inbuilt machinery in classical mechanics which handles indistinguishability of particles. So, we will see how quantum mechanically starts off with this correct formalism as if it is embedded in its DNA. Okay. So, the n factorial is not going to be missed, in fact it will be plugged into your calculations from the beginning itself, that is number 1. So, in the context of indistinguishable particles we will be discussing two types of particles, which are fermions and bosons. So, basically these are particles with some half integer spins. Okay. So, you can take spins and so on and so forth, and for bosons we will have integer spins. So, the fundamental particles or the fundamental indistinguishable particles are classified into fermions and bosons in the quantum mechanics, and they are basically different from each other in the sense that one corresponds to the parity operator having eigenvalue +1, and the other corresponds to the parity operator having eigenvalue -1. Okay. So, P here is the parity operator, and I will talk into some detail about this operator, and we will also basically see that quantum mechanics does the correct counting or correct enumeration of states naturally. Okay. So, this correct counting of the micro states is natural in the quantum mechanical formulation. Basically what is meant here is that when you have an n particle system, you do not start your calculation by just doing any deterministic calculation. What you do is write down an n particle wave function, and the properties of this n particle wave function, by property I mean whether the wave function is symmetric under permutation of n particles or not, decides whether it is a bosonic wave function or a fermionic wave function. And this symmetry of the wave function in terms of permutation of particles demands that the fermions obey exclusion principle. So, the last point that I would like to mention here is that a consequence of the symmetrization of the wave function or the anti-symmetrization of the wave function, fermions obey Pauli's exclusion principle, and no such restriction is there on bosons. Okay. So, a couple of things that we should so this is basically our menu of topics that we would be covering, and if you are doing quantum statistics, I believe there should be a nice understanding of, first of all, why we need quantum mechanics, where is it that we are lacking in terms of a classical understanding of the system. Then once we present a case for quantum mechanics, we must allow for a discussion on various types of particles, which are the fermions and bosons. We will discover that these two types of particles are nothing but the consequences of your wave function, overall wave function being symmetric or antisymmetric in terms of a parity operator. Okay. That is why we call them fermions and bosons. It is just a definition. Okay. Then after introducing this definition, we will show how it does the correct counting of microstates, which is natural, or in some sense I keep saying that quantum mechanics is sort of on the start, on the word go, does the correct counting of microstates. I will explain why is it so, and as a byproduct of this correct counting, it also basically shows why fermions will obey Pauli's exclusion principle. That is no two fermions can exist in the same single particle quantum state. Okay. Because if you try to force two fermions in the same single particle quantum state, then the entire wave function of n particle system will collapse to 0. When you say that the wave function is collapsed to 0, you mean you are saying that explicitly that microstate has 0 probability. So, you will never see this simply. So, that is the sort of a sketch or the bird's eye view of what I am going to present in today's lecture. So, let us start with the first point on the menu, which is onset of quantum mechanics. Now, we have seen in the second chapter that we had a length scale which was called as the thermal de Broglie length scale. Okay. So, recall that there was a thermal de Broglie length scale. Now, I call it as it is a length scale, and I am calling it as a thermal length scale because it is associated with the temperature of the system, and depending upon how large or how low the temperature is, the length scale will vary. You can call it de Broglie wavelength or de Broglie length scale, whatever comes to your mind. That is not necessary, but its form was we had discovered that this length scale is the Planck's constant h over 2 pi m kBT, where kB is the Boltzmann constant and T is the temperature of your system, h being the Planck's constant. Okay. Now, I had said that every system that you study, let us say n particles in a box or electrons in a metal or gas in this room, you have a certain container or you have a certain box where your particles are they exist. So, I know that my system has a density . I call it as small n, number density, which is the number of particles in the system over the system's volume. Okay. So, now you can see that this density has the units of it has the units of just L to the power minus 3 because of volume. Now, like I said in the beginning a few lectures ago, that if you want to see the nature of the system, we can always construct a few interesting dimensionless numbers that will tell us how my system will behave. Okay. So, with one length scale lambda, I am going to construct another length scale from my density and compare these two length scales by constructing a dimensionless number. So, straightforwardly I can construct one dimensionless number, construct a dimensionless number . Okay. You are free to construct other numbers also. By the way, you can also construct another lambda. So, you can take lambda as one length scale, our de Broglie length scale, you divide it by some density dependent length scale. This is another dimensionless number. Now, how do I construct this lambda n? This lambda n is it can be taken as some n to the power minus 1 by 3. But since we normally work with density, which is known to us, for example, for copper, I know that the number of electrons in the metal, free electrons, is of the order of 10 to the power 28 per meter cube. I know the densities, I know the density of hydrogen in this room. So, I would like to work with this combination of this dimensionless number, where I know n from handbook of materials or by previous laboratory experience or whatever, and I know to a very good extent what is my de Broglie wavelength. So, I can choose to work with this dimensionless number, okay, purely for convenience sake. So, let us pick up this dimensionless number and see whether we can distinguish the two worlds, quantum and classical. So, clearly I know that the limit of high density and low temperature is the quantum mechanical world, because this is where when you take when you look at the expression for the de Broglie wavelength, this wavelength will be very large at very low temperatures. As the temperature goes to 0, lambda goes to infinity. So, the wave nature of the particles becomes to dominate, it becomes essentially more and more delocalized. So, I know that for low temperature is the quantum regime. I also know that if I for any temperature I can increase my density, thereby making the interparticle separation smaller and smaller in such a way that this separation can be made smaller than the de Broglie wavelength. That is also a quantum limit for my system. So, one thing is clear, that the dimensionless number n lambda cube being much larger than 1 is the quantum regime. The regime where I make both n and lambda larger and larger, okay. Because lambda is large means my wavelength is getting large, my wave nature of the particles becomes more and more predominant, and density being large means my interparticle separation is also much smaller than the de Broglie wavelength. So, this is definitely a quantum regime, okay, and we will I will show by calculating numbers this is definitely quantum regime. I also know that well, just by the preceding argument we can push this limit to the other side. So, I can say that if this dimensionless number is much smaller than 1, okay, then I am in the classical regime. Of course, because I can push n lambda cube to be much less than 1 by making n very very small, thereby increasing the separation between particles such that the particle separation far exceeds the de Broglie wavelength, okay. And lambda is also being very is made very small, which is like increasing temperature, because lambda is proportional to 1 upon square root t. So, both n and lambda are increased, that increases n lambda cube, and both n and lambda are reduced, that reduces n lambda cube. It is very simple to see why one leads to a quantum effect, the other leads to a classical behavior. Naturally, there is a boundary that separates these two, and the boundary is not sharp, the boundary is fuzzy, okay. And I will say that n lambda cube of the order 1 is the onset of quantum mechanics. Okay. So, this is where you will sort of say that I am not very clear which theory will work, but I am sure that the quantum effects are not ignorable, and n lambda cube is of the order 1. It is tricky, it is not easy. It is very safe to handle the two extreme regimes, where the regime n lambda cube being much smaller than 1 almost guarantees that your classical calculations will work with, they will come out with flying colors. In the regime n lambda cube greater than 1, classical theories will fail miserably, and this is the regime where you have electrons in a metal. You must invoke a quantum calculation, okay. For electrons in a metal at room temperature 300 Kelvin, you will very soon calculate that n lambda cube is much larger than 1. So, you must invoke a quantum calculation. All your d by your Dulong-Petit's law will fail miserably for heat capacity of a metal due to electrons. And when this dimensionless number is of the order 1, you know that you have to be careful, because this is the regime when quantum mechanics begins to show its presence. So, then you can actually construct some sort of a parameter space diagram, where at least figuratively you can say whether quantum mechanics applies or quantum mechanics or classical mechanics applies. So, you can say that I will consider a T n diagram, number density versus temperature, and show in which the region of applicability of classical or quantum mechanics. Clearly, there is a line of 45 degree slope, which is the T equal to n curve, okay. And my curve n lambda cube equals to 1 would be somewhere like this. So, this is my curve okay. So, deep inside this phase, so this curve that I have computed, the solid line, is the line of n lambda cube equal to 1, okay. And deep inside this phase you will say that your system has quantum effects, because that is the region when you have high density and low temperature, and deep above this solid line you will say that I have a classical regime. Okay. And somewhere close to the n lambda cube equal to 1 line you have a onset of quantum mechanics. So, I will say I am going to remove the t equal to n line, because it is making the figure very busy. Just maybe very faintly I will show. Okay. So, this is where I have the onset of quantum mechanics near the solid line. Okay. Just to give you a feeling in terms of numbers. So, if I compute the, I will say that, so at what temperatures do I see quantum mechanics? So, if that is the question, at what temperatures the quantum mechanics begins to take over, well, you have this relationship. So, if that is your question, you can answer this by saying, okay, this is the fuzzy boundary n lambda cube equals to 1. This will give me the temperature when quantum effects will begin to take effects, and I know this is nothing but n times h cube over 2 pi m kBt to the power 3 half, because that is the definition of lambda. So, now you can compute the temperature from here. So, you can say that my kBt, and this is nothing but the, in some sense, the degeneracy temperature, where this particular T is when n lambda cube is 1. So, I am just calling it as T naught. So, if I take kT on the other side, I will get kT to the power 3 half as n times h cube over 2 pi m to the power 3 half, fine. Just multiplied both sides with kT to the power 3 half, and this gives me kT as nothing but n to the power 2 by 3 into h square over 2 pi m, okay. And naturally if you compute, so if you just, you can write down this, you can divide it by kb on both sides. So, So, this is the basically the temperature that corresponds to your n lambda cube equal to 1. So, this is the temperature at which quantum mechanics will begin to take effect. Let us compute these temperatures for some of the systems that we routinely encounter in our everyday lives. It will give you an idea, you will appreciate the fact why should I learn quantum mechanics. Okay. So, I am going to take some examples. The first example that I am going to take is that of hydrogen. So, hydrogen for instance has a density, and I have written it down here, has a number density of 2 into 10 to the power 19 per centimeter cube. So, this is the number density for nitrogen. Okay. So, this is the N for nitrogen. Now, if I want to compute the degeneracy temperature, so this gives me the degeneracy temperature. If I compute this, it comes out to be around 5 into 10 to the power minus 2 Kelvin. So, somewhere around 0.05 Kelvin for hydrogen, you must invoke quantum mechanics, or you must invoke quantum statistical mechanics. So, a classical calculation is perfectly valid at room temperature. Okay. Only at this low temperature your n lambda cube is of the order 1. That is the meaning of this calculation. Okay. Let us take another, is there a question? Which tells you what? See, I computed this temperature by equating n lambda cube as 1, which is the onset of quantum mechanics. So, at this temperature you will see quantum mechanical effects. Higher temperatures definitely I will be classical. Okay. So, unless you push your temperatures down to 5 into 10 to the power minus 2 Kelvin, which is like 0.05 Kelvin, you can treat hydrogen in the air classically. Let us take another system, which is helium 4, liquid helium. Okay. So, this has a number density of liquid helium has a number density of 2 into 10 to the power 22 per centimeter cube. Now, this is a higher density. So, I can expect that the degeneracy temperature will be higher, because now I should see quantum mechanics effects at even higher temperature, because this guy is already sitting at a higher density. Okay. So, this is the N for it, and you plug this number density in this expression that we have computed, put the value of Boltzmann constant and Planck's constant, you will find that the degeneracy temperature for liquid helium is of the order of 2 kelvins, which is in some sense 100 times higher than the previous guy. Previous guy was of the order 0.01, this guy is of the order 1. So, already by boosting density I have actually made quantum mechanical effects come sooner. So, I do not have to go all the way to 0.01 Kelvin now. Going by this logic, you can expect trouble to come if you go to electrons in a metal. Why these heat capacity expressions given by Dulong and Petit do not work for metals even at room temperature? It is because of this. Let us do this calculation also. Now, you take typical copper for example, copper, which is a perfect perfectly good example of a metal, and each copper donates one valence electron to the matrix. So, a number density of typical copper block is of the order of 10 to the power 22 per centimeter cube, which is my density, that is per meter cube. Okay. So, if you take this number density and do this calculation, you will get, well, as expected, because now I will get a degeneracy temperature much higher. This degeneration temperature comes out to be 10 to the power 4 Kelvin. The reason why the two degeneracy temperatures for liquid helium and electrons in the metals are so different, the electrons in the metals having such higher degeneracy temperature in spite of the fact that both had the same number densities, because helium 4 has a much higher mass, okay, roughly 8000 times heavier than electron, because it has 4 nucleons. And so, that is the reason why you have such different degeneracy temperatures. But the thing to see here is that for electrons in the metal, the degeneracy temperature, that is the temperature where quantum effects will arise, is 10 to the power 4 Kelvin. This tells us that at room temperature, which is much below 10 to the power 4 Kelvin, we must invoke quantum mechanical theory to correctly understand heat capacity of solids due to these free electrons. So, any theory that we invoke on electrons in metals has to be quantum mechanical. These electrons are heavily quantum mechanical at room temperature in the solid metals. Okay. So, that is the, that is, this basically gives you a feeling of the numbers, that I must invoke quantum mechanics when I am dealing with electrons and metals, because that is a degeneracy temperature. 300 Kelvin is for sure much lower than 10 to the power 4 Kelvin. Okay. So, only when temperatures are much higher than 10 to the power 4 you can use a classical theory of electrons in metals, but then at those temperatures you do not have a metal, you will probably be making a gas out of a metal. Right. So, now let us proceed with the second topic in the agenda, which is if we go back, the statistics of indistinguishable particles. Okay. So, indistinguishable particles are handled very carefully in quantum mechanics. For example, if I take just the 2 particle system, one sitting at somewhere location R1 and another sitting at location R2, just take the 2 particle system. Okay. So, I am just taking a 2 particle system. Then I can write down the wave function of my system as of the 2 particle system as psi of R1 R2, and is the system wave function. I will show how to write down psi, which is the overall wave function, in terms of single particle wave function in a short while. But I know for sure that if I permute these 2 particles, that if I make R2, the second particle go and sit on R1 and the first particle go and sit at R2, the Hamiltonian of the system does not change, okay, because the Hamiltonian of the system is a function of potential energy and kinetic energy, and clearly if the particles are indistinguishable, I am not affecting their potential energy in any way, because they are the same particles. So, permutation of 1 on 2 does not change the potential energy, and it clearly does not change the kinetic energy, okay, because I am just putting one particle having some kinetic energy at location which is different, its kinetic energy remains the same. So, Hamiltonian does not change. Under permutation. Of particles, okay. Meaning what? The energy of the system remains the same under permutation of particles. This essentially means that if I take the Hamiltonian operator and this and operates on the particle 2 particle wave function, the eigenvalue, which is the total energy of the system, does not change if the particles are permuted. Okay. That is the meaning of the Hamiltonian operator, which means if I think of a parity operator, P being the parity operator, whose action is to just permute the particles, okay, then I do not expect to see any change in energy, which means the parity operator, when it acts on the system, makes the wave function basically psi of R2 R1, simply swaps the two particles, that is the effect of the parity operator. And I know from what I have written here that the Hamiltonian of the system must not change, which means the energy of the system should not change, which means if I apply the Hamiltonian operator on this new wave function P of psi, okay, R1 R2, considering this as my new wave function, okay, then I must get the same energy because the energy has not changed. Okay. So, the same wave function comes back without any change in the energy. This E is the same as this E. Okay. But I can also write this as I can also consider P operating on H psi, okay. So, this is my new function. This is nothing but P H on psi simply gives me E times, that is the eigenvalue psi R1 R2, but E is just a number, it is the eigenvalue. So, I can write this as E times P operating on psi R1 R2, which is nothing but psi R2 R1. Okay. You can compare the previous equation, this is also E of multiplied to psi of R2 R1. So, if these two are same, I can say that by looking at these two, the left hand sides, that my Hamiltonian operator commutes with the parity operator. I can say that the product of these two operators is the same as product of P and H, implying that the Hamiltonian commutes with the parity operator for our identical particle system or indistinguishable particles. And this has very important consequences. This is why quantum mechanics does calculations correctly. Okay. This is the birth of the correct enumeration of states. In a very logical sequence of steps, I showed that the Hamiltonian of the system commutes with the parity operator. This brings us to the stage that I can write down now the effect of my parity operation done twice. I already know that P simply swaps the positions. So, P operating on psi R1 R2 simply gives me the same wave function now, but the particles permuted. If I do not know what is this new psi, I can compute this new psi by operating P again, which is nothing but P square operating on psi R1 R2, okay. But I already know what is P operating on psi, which is my psi R2 R1. So, one more operation of P on this will give me back the old function, it will bring the system back to the old state. You made 2 go and sit in 1, you do one more permutation, you get back the same old wave function. So, definitely my P square has an eigenvalue which is 1, and the fact that permutation, you have seen that here that the Hamiltonian permutes with the parity operator tells me that a permuted wave function has the same energy and hence it is the same state as the previous state. If there are no degeneracies, okay, then there are these are the same state, because it has the same energy, same Hamiltonian, which means p psi and psi differ only by some constant prefactor. Okay. It is just the same, because if I take p psi and psi, they should be differing only by a constant prefactor. So, the eigenvalue equation is not moved, you have the same prefactor on both sides. H operating on p psi will giving me some E operated on p psi. They are the same, you know, if p psi differs from psi by just a factor, you are looking at nothing but H psi equals to E psi. Okay, you can knock off that constant prefactor both sides, which tells me that my operator p should have the eigenvalues plus or minus 1. That is the only way I can make p square 1. Okay. Now, this basically leads to two definitions. So, if you have, you can define particles or system of particles which have the property of the action of parity operator on the whole system, giving an overall positive sign, which means it is not affecting the system, as a system of bosons, and define the other type of, there is only two possibility plus and minus 1, as a system of fermions. And this is only a definition. By the way, you can swap the definition, you can call p plus 1 as fermions and p minus 1 as bosons, and everywhere your fermions will obey the Bose statistics and bosons will obey the Fermi statistics. So, this is what is in a name. What is basically to be realized that these types of particles in the due course will be shown to obey a statistics of average number density going as 1 upon e to the power beta some jth level is E j minus mu minus 1, and these guys will be shown to have statistics which is 1 upon e raised to beta E j minus mu plus 1. What is essentially is that this should match with this and this should match with this. You can call bosons and fermions either way, I do not care, but the guys that commute with the parity operator, the wave function of the guys which commute with the parity operator and for which the parity operator has an eigenvalue plus 1, I will call them as bosons for historical reasons, and they will be shown to have statistics which go like this, and the other guys will have statistics written below. Okay. You can call whichever what you want, but historically we call them the first class as bosons and the second class as fermions. So, it is important that this map is between the values of the parity operator and the correct statistics. Okay. Now, we can write down the wave function of the system, this two particle system, as some kind of a linear combination of single particle states. So, I will take what do I mean by single particle states is the following. So, let me first write down the single particle, so draw a figure. So, to write psi, we consider two single particle states. So, I have one particle at location r1 and another particle at location r2. Meaning of single particle state is that I can consider two localized wave functions at the location of r1 and r2. So, maybe you have another wave function which is localized at r2, call the first one as phi 1, call the second one as phi 2. Classically you have a particle there at r1 and r2. Quantum mechanically it is represented by a wave function which is localized around r1 and r2. Okay. So, it is non-deterministic quantum mechanics. So, I must, if there are n particles in this room, I have n single particle wave functions, each one of them localized around the particle, physical location of that particle. So, you can write down psi in terms of these phi. So, these phi i's are basically the single particle wave functions. As simply some normalization constant into, the only linear combinations that you can construct basically are products of phi 1 and phi 2. So, I will take phi 1 r 1, which is like the first particle sitting at location r 1 into phi 2, because this is the joint probability. So, the fact that my system has two particles at r 1 and r 2 is given by the joint product of phi localized at r 1 and phi 2 localized at r 2. Okay. Is that it? For two particles, I have one more possibility, that the second particle can sit at r 1 and the first particle can sit at r 2. So, that is given as phi 1 r 2 into phi 2 r 1. See, phi 1 and phi 2 are localized wave functions, one localized at r 1, the other localized at r 2. We have simply swapped the particles. Okay. This is for bosons. If I were to write down this wave function for fermions, I have to take a negative sign here. Why? Because if I take a positive sign, then that would mean that under permutation of the particle, the wave function is not incurring any overall negative sign, which means plus sign has to be for the bosons. And if these two particles are fermions, then under permutation of the two particles, the overall wave function should incur a negative sign, and that is only possible if I write down the second product with a negative sign. So, now you can see for fermions, if I swap r 2 with r 1, so for fermions, so if I apply the parity operator on r 1 r 2, this will give me a times phi 1 r 2 phi 2 r 1, and I have to take the minus sign, minus phi 1 r 1 into phi 2 r 2, but this is nothing but minus of my original fermionic wave function. Okay. So, this is what I expect. Similarly, for bosons, if I apply the parity operator, then I get back the same function, phi 1 r 2 phi 2 r 1 plus, because I have a plus sign for bosons, okay, already given here. Okay. Plus phi 1 r 1 into phi 2 r 2, but this is nothing but the old wave function. So, that is why for fermions I had to take a negative sign. Now, you can generalize this for 3 particle system, 4 particle system, n particle system. So, you can always write down the n particle wave function by choosing one product and simply doing permutations of these products, and this way you can write down it in the determinant form, which is called as the Slater determinant form. For the 2 particles, I can thus write down what I have written for the fermions only. For bosons, you cannot write using the determinant form. For bosons, you just have to use a plus sign throughout. So, for 2 fermions, that we have just discussed, you can write down these this wave function also in the determinant form. What I have written here, this particular this equation, a times phi 1 r 1 into phi 2 r 2 minus phi 1 r 2 into phi 2 r 1 in the determinant form. So, you can write it as a times a determinant phi 1 r 1 okay. And similarly for 3 fermions, or I would say for n fermions, let us write down for n fermions directly. You can write this n particle wave function as some normalization constant. Okay. I will call this as A2 for 2 particle normalization, and this I will call for n particle normalization as phi 1 r 1 the last row being phi n is called as a Slater determinant of form for historical reasons. Couple of things to be sort of kept clear here is what is this normalization constant. Okay. So, we can work out the normalization constant by, and this will give us the n factorial logic. You see, for 2 particles, how many combinations could you construct? 2, 1 2 and 2 1. With 3 particles, you had 6 because that is 3 factorial. So, with n particles I can construct n factorial permutations. So, this normalization constant is fixed. Okay. So, these A is are fixed by the normalization that your integration over the entire volume. Okay. So, I will take volume I going from 1 to n d cube r I, psi is now n particle wave function. Okay. Psi psi star is equal to 1. This is my normalization. So, volume integral of psi star is 1. Okay. So, for example, in 2D I can think of A2 as just 1 upon factorial 2 to the power half, because when you do a psi star, this will become 1 upon factorial 2, and precisely so the normalization on single particle wave functions also need to be specified here, and I am going to write down with this single particle normalization is given as and that is very simple to see why you have the sort of a orthogonality of these single particle wave functions. So, this is the orthogonal scalar product. Okay. So, the orthogonality of the functions are basically represented as this integral phi with its complex conjugate given as the Kronecker delta function. Okay. That is the meaning of this orthogonality. You can check. Okay. So, for the simple 2 particle case, 2 fermion case, you had your psi r1 r2 given as phi 1 r1 phi 2 r2 minus phi 1 r2 phi 2 r1, and I have to take the normalization as 1 upon square root of 2 factorial is 2, it becomes very clear why, because of this norm. So, I have these orthogonalities of the single particle wave function that gives the norm as 1 upon square root n factorial. So, you can write down the normalization condition as now you have 2 particles. So, you do a double integral. So, you do one integral on r1, second on r2. Okay. You can do a d cube r1, d cube r2, psi star. Okay. So, you take one psi from the right hand side and the star of it will give you another 1 by 2 factorial. So, there is a 1 upon 2 that comes outside, and what you have is basically phi 1 r1 into phi 2 r2 multiplied to its own complex conjugate. Okay. So, I am going to write down phi 1 star r1 into phi 2 star r2. Okay. This is multiplied to its own complex conjugate, and the second term also multiplied to its own complex conjugate. So, that will come with a plus sign now, because minus minus plus. So, this will be phi 1 r2 the cross terms by virtue of this orthogonality will disappear. So, whenever you have a cross multiplication, say you have a phi 1 r1 into phi 2 r2 multiplied to phi 1 star r2 and phi 2 star r1, that will go to 0, because on one integration coordinate, if the phi I and phi j are not the same, this Kronecker delta function will be 0. Okay. So, you have only 2 terms that will basically contribute, and I can write this as now 1 upon 2. The first term can be written as integral on r1 d cube r1 phi 1 r1 into phi 1 star r1 into integral r2. I can simply write down this as a square of this okay, because these are independent integrals plus integral on r1 I can do this integral on r2 if you want. If I want to do it on r1, then I have to choose phi 2 here. okay, and the other integral is basically a definite integral the same type. So, there is nothing but the square of this integral. Is it okay? Because R 1 and R 2 are independent, I can write a square of that, which is nothing but 1, because each one of them is 1 from the orthogonality. So, this is how I am going to write down the normalization prefactors. So, for these a n, I am going to write down 1 upon n factorial square root, and for a 2 I am going to write down 1 upon 2 square root 2 factorial. Okay. So, now you can see if I just use this n particle wave function, I can see how Pauli's exclusion principle naturally arises. Can you see why? Can you see why? So, suppose so from this n particle wave function, which is written in the form of a determinant, I can simply use a property of a determinant. If two rows of a determinant become same, then the determinant collapses, which means if some random ith row becomes the same as the jth row, let us say phi 2 row becomes the same as the phi 3 row, then the determinant will collapse. So, the n particle wave function will collapse to 0, okay, which actually is the mathematical statement of the Pauli's exclusion principle for fermions. Okay. Now, I must not write down n particle wave function, I must be very specific that this later determinant is a n fermionic wave function. Okay. So, that is the region of Pauli's exclusion principle, that you cannot force two fermions to occupy two identical single particle states. So, if two single particle states I and j, phi I and phi j become the same, then the entire wave function of the system will collapse, and that microstate has 0 weight in your macrostate. Okay. Two fermions cannot occupy the same single particle state. Because that would simply make two rows of my slated determinant identical. Okay. And for example, for a two particle system, it is very simple. Okay. For psi r1 r2, it is very simple to see why. It would simply make I have got a 1 upon factorial 2 outside, right, which is 1 by 2, and I am going to write down phi r1, phi phi 1 r 2, and I made phi 2 as phi 1. So, this becomes phi 1 r 1 and it becomes phi 1 r 2. This is 0 determinant. So, this is the fact that your system had an odd parity, you could write it as a slated determinant, and because you wrote it as a determinant, and the fact that you cannot write two rows and determinant which are identical without making the determinant itself 0, gives this Pauli's exclusion principle that is seen in quantum mechanics. So, it it's an linear algebraic consequence of doing a quantum mechanics on these indistinguishable particles. So, that is the end of our lecture. In the next class we will carry over from here and provide two different statistics for these so called different types of identical particles, the fermions and the bosons. We will show how are the statistics derived from first principles in these two systems. In this class we have only discussed why we have two different types of statistics, because of the